Good day everyone. Today we are going to talk about the Fourier series. And in previous video, we see how we can analyze function in a given plane. We also talk about the integral theorem and all that. But today's video, we are going to be treating a very different aspect, which is the Fourier series. And in the Fourier series, I would like us to start by analyzing the periodic function. Now, we said a function is said to be periodic if the function plus its period 2 pi is equal to the function itself. If you have this condition, then you can conclude that the function is periodic. If, for example, we have this is a sine graph. And the sine graph, of course, it starts from the origin. And from the origin, we have a semicircle or half revolution, which is pi. And we see that from here to here is 180, and from here to here is another 180. And of course, pi is 180. So 180 plus 180 will give us 360, which is the complete oscillation. So we have that for the sine graph, we have that sine is periodic at 2 pi because we have 2 pi to give us a complete oscillation. This is the graph for sine function, and also this is the graph for cosine function. And we have from here to here is not a complete oscillation. We have just pi over 2 because from here, if from here to here is pi, it means from here to here will be pi over 2. Then from here to here also will be pi over 2. And then pi over 2 plus pi over 2 will give us pi. So if for the sine graph, we start from the origin to pi, and also to complete the oscillation, we start from pi to 2 pi, because if from here to here is 180, from here to here must be 360. So this is the graph of sine x, or sine x, where x are a period pi, 2 pi, 3 pi, 4 pi to infinity. And also for the cosine function, we have from here to here is pi over 2. It means from here to here also will be pi over 2. Then from here to here will be pi. So if from here to here is pi over 2 and from here to here is pi, then we need another pi over 2 to complete 2 pi, because pi over 2 plus pi plus another pi over 2 will give us 2 pi. So it means from here to here is 2 pi, because from here to here is pi over 2, and from here to here is pi, and from here to here is another pi over 2, which is 2 pi. So if you just add it up, pi over 2 plus pi over 2 will give us 2 pi, which is the complete oscillation for the cosine function. So having seen that this is graph for cos x, the graph of cos x. So let's move on to non-sinusoidal function. But first of all, take note that a function whose period is 2 pi is said to be sinusoidal. So in case you have any function and you observe that the period of the function is 2 pi, then you can conclude that the function is sinusoidal. But what if we have a non-sinusoidal function of this form? We have from 0 to 6, 6 to 8, 8 to 14, 14 to 16, and the period there is in seconds. So let's find the period of each of these functions we have here. And of course, the function is a function of t. So you can say y equal to f of t, and where t is in seconds. So let's find the period of this first function. We have that the function starts from 4. From 4, we have 6, 8, 14, 16. So how can we find period of this type of function? First of all, you need to check where the function start from. And of course, the function start from 4. So having noted the point where the function start from, look for another similar point in the function. Then any place of such, then you can conclude that that is the period of the function. So we have that at 0 on the y-axis or the f of t axis, we have 4. It means that this function starts from 4. And on this diagram, the only point where we have similar origin or similar start point of 4 is at this point here and also at this point. So at this point, we have to trace it down. If we trace it down, we have 8. So it means that the period is equal to 8. That's just how to find the period. So 8 plus 0 to 8 plus another 8 will give us 16 plus another 8 again will give us 24. Then also for the second graph, we have that the function starts from the origin and is going this way. We can actually find the period of this function using different method. But the method I would like us to use is just to analyze this graph. So we have this line starting from the origin going towards the positive y and the positive x axis, or in this case f of x and f of t. So where we have similar start points is at 6, because we have from 0 to this way and we also have from 6 going this way. So it means the period must be 6. Period is equal to 6 seconds, please, 8 seconds. And for the last one, we have the start point from 4 going this way. Where we have similar start point is at 5. If you can observe where we have the function going this way, and we also have the similar function also going this way. So it means that this is where we have the similar function. And for this case, we have it here. We have it here. So it means the period of this function must be 5. So we can write that the period is equal to 5 seconds. So that is how to analyze a periodic function. Just know where the period starts from and look for another similar point that is of the same start point of the function. Then where you have that point is the period. Like for the first function, we have it at this point at 4. So if we move to the next one, you have it here. Move to the next one, you have it here. So you just trace it down. The point there is 8 plus another 8 give us 16. So the period is 8 seconds. And for this also, we have here the origin. So if you also trace it, we have it here also. Because this triangle is similar to this triangle. So the period is 6 seconds. And for this also, we have 4 here. This is the start point. And we also have another one here. And we also have another one here. So if this is 0, this is 5 plus another 5 will give us 10. So the period is 5 seconds.